that seems a bit premature. You don't know what I'm going to say yet. Good evening, everyone. Thank you for coming today. It's really, really lovely to see so many of you. That, yeah, I thought it was all going to be Neo4j employees and like one poor guy stuck in the middle thinking, who are all these database weirdos? So it's nice to have a spectrum of humans and the occasional Dane. Oh, there's two of them now. Hang on. Safety check. Who's from Copenhagen? Who's from Greater Copenhagen? Oh, that's you lot. The rest of you. Okay. So, hello, I'm Jim. I work at Neo4j, and a few of these guys around work at Neo4j. And we're a bunch of database nerds. And so tonight, what I want to talk about is, don't worry, there's not going to be any like complicated stuff. I'm not going to like quiz you on algorithmic complexity or any of that stuff. I'll save that for the job interview. I'm going to talk about some fun stuff about the history and future of graph data. And in fact, there's a bit of distributed systems in there. There's some Star Wars. There's some swearing. It's like a good mixture of all-round good stuff. The swearing will be in English exclusively, which means it doesn't really count. Apart from for you, for whom it does count, but you're used to it by now, mostly. Inventive swearing. So there's like 3 bits to the talk, and I've helpfully categorized them in celebration of episode 7. I helpfully categorized them in ascending numerical order 4, 5, and 6. So I want to talk about how graphs came about how databases came about, and then by implication how graph databases came about. That's what Neo4j is, of course. I want to talk about where we are kind of today in graph databases. In fact, in distributed systems generally, actually, we've got some really interesting and slightly dark stuff about reliability, availability, and of course, just as in Empire Strikes Back, corruption. So there's a kind of dark middle bit to the talk. It's kind of like your Nordic noir. It's kind of the Sarah Lund bit, if you so like. Jolly nice jumper, by the way, Magnus. Nobody else is wearing one. Not even the other Danes. I thought it was kind of uniform for you over-the-bridge folks. And then finally, we'll do the kind of upbeat stuff at the end, and I will get something off my chest. So here we are, back in the day. These guys are like, the 1970s? There wasn't even any JavaScript then. So back in the day, I was born at this point. That's okay. Several of you weren't. That's troubling, actually, as I get older. The fact that cultural memes no longer work. Anyway, back in the 70s. So what happened, right? Back in the 70s, like the world that we lived in was kind of square, right? So we all, at least from a data perspective, kind of, we had data processing, computers as they became known, but everything they processed was kind of regular and uniform. So we all had the same kind of payroll data, and we all had the same kind of social welfare data, because remarkably we had social welfare back then. And we all had, everything about us was the same. We were very homogeneous, we were very square. And it turns out that was actually quite useful, that we were all very similar, very, very uniform, because that fit the data model that emerged in the 70s. So in the 70s was when the relational model first arose, and of course when we first started to understand the notion of processing tables. And that was a fascinating time. In fact, but having said that, the 70s weren't all brilliant. I mean, there were some bits of the 70s that were a bit shit. Obviously, there was a little bit of the kind of homogeneity breaking down in the 70s. In fact, this is Birmingham, Michael. Do you recognise it? It's in my hometown that Michael just inadvertently told me, what was it? A shithole with bad air. I think he meant a shithole with bad hair. I love this. So this is a calf plant. This is the Longbridge plant. These guys, as you guess, are all on strike. There's one guy on here who I love more than all of the others, and it's this guy. Right, this guy, he looks like my uncle, actually. He's so on strike, he's not even taking his hands out of his pockets. He's like the most on strike guy. I love that. Anyway, so in the 1970s, the relational stuff took hold, right? Fast forward to the 1980s, and she's dead. She ruined my childhood, what can I say? I owe her, big time. So fast forward to the 1980s, and that stuff that started off as a research project in the 1970s becomes the dominant paradigm. It becomes the dominant data paradigm. In fact, in 1986, 1987, Oracle becomes like the world's largest software behemoth, blah, blah, blah. So this thing that started off as Codd's research project, initially commercialized by IBM, goes rampant in the 1980s, and it is the decade of the relational database. And boom, they are suddenly everywhere. And we're processing the tables and doing the joins somewhat slowly, but we're doing all that stuff that we recognize today as data technology. And of course, then this then continues, throughout the 90s and even the first decade of this millennium, whenever we say the word database, we all know what that means. It means relational database. And in fact, there's even a special Visio symbol, the little can of beans symbol, that means relational database. And even architects understand that. Architects, carefully, oh, you know the Visio symbol I mean, right? That's one of your most used, that's in your like most used Visio symbols, can of beans. Good, good, good. So that thing's spread everywhere. And I think we've done really brilliant, ambitious, and marvelous things with this technology. And this is good technology, by the way. This isn't some like, like dodgy cowboy technology that some like random dudes in Sweden invented and tried to commercialize. Oh no, other way round, right? Other way round, boss. We've done amazing and complicated and scary things. Thank you, by the way, for sending over the schema. That was really useful. No! Some of you are super clever and super good at relational databases, right? Not Johan, obviously. He had to invent an entire new kind of database because he sucked at this shit. But some of you can see through this database, this schema, and you can see the intent. Right? I can't. I look at this and I'm like, fuck that. But some of you are like, yep, I can see the data model kind of emerging in front of your eyes. Like you can see through it's like the Matrix thing. See what I did for you? You can see through the kind of telnet screen and you can see the kung fu. I can't. This stuff is amazingly complicated. And actually, I think our ambition has grown to the point where we are building systems of such sophistication that we're starting to outgrow what the relational model can give us, and therefore we're starting to find that tables, and particularly joins, are not the be-all and end-all. And it turns out that relational databases are complex, even for simple things, and we don't see it because we're so used to dealing with that accidental complexity. Even to express simple things like end-to-end relationships, you have one of these things. What's this? Join table, link table, yeah. The first time I learned databases, I didn't actually have a physical database. It was like a pencil and paper exercise. Seriously? Thanks, man. I just, this guy is just like giggling at me for being like some old fart who uses a pencil and paper. When did that happen? Because I used to be this guy, like laughing. Anyway. And I learned this like relational algebra, and it kind of made sense and blah, blah, blah. And then I got to my first database on a time-sharing Unix system, and it was Ingress. And then like the professor teaching me, who's awesome and lovely, was like, yeah, you have to actually have this join table. And I can't tell you how angry I was. Well, you can imagine, right? I'm kind of an animated person. How absolute... Why do I tell the database how to do its fucking job? I didn't say fucking because it's a professor and I want to pass the course. But that was the semantic intent. I was like, why is this my problem? And he's like, it just is. Deal with it. Stupid join table. And I know that these things cost in a relational database. And I know that they cost disproportionately compared to the data set size. And I know that this idiom is everywhere in your schema, because we're trying to model an increasingly interconnected world. We're not modeling, the world as a set of discrete tables that never interact. You guys are all Nordic folk. In the 70s, we never interacted, but now suddenly in your data, there's a few random Brits and we're here talking about databases and blah, blah, blah. It's all getting mixed up and complicated. And if we try and model it this way, well, it just gets fundamentally hard. We get some kind of join bomb problem, which is an awful, awful thing. One more. You watch the video, I'm drinking. So fast forward into the 1990s, so we get out of the 80s, into the 90s, and people are starting to think about data differently. So there's a guy called Tim Berners-Lee who invented this thing called the World Wide Web, which is brilliant because we get porn, and he was starting to think about data very differently. He was starting to think about data at enormous geographic scale. That's the worldwide bit. But he was also thinking about the data as being interlinked, not joined in some kind of Cartesian product of sets kind of way, but interlinked in some domain-specific, meaningful way that you can kind of follow, from some index. You could get into some site about the English Midlands and then find Birmingham, then find wonderful glowing reviews about Birmingham and how lovely it is as a city to grow up in, even in the 1980s. And then something else changed around the turn of the century, and people started talking about Google scale. So big stuff started to happen. And the really interesting thing about this stuff is that it wasn't necessarily a relational database. So you think about some of the more famous precursors to NoSQL, and for example, Amazon's Dynamo. And it's weird, right? Because Amazon at this point in time is nothing more than a bookshop. It wasn't the kind of tech behemoth that we know it today. It's a bookshop on the internet. And so instead of just using Oracle, as they obviously should have done, at some point they said, actually, the most important thing that Amazon can do is always make sure you can put something in your basket. I mean, from my point of view, the most important thing they could do is pay their fucking tax. But from their point of view, it's you can always shop. It's very American, isn't it, that? You must always consume. And so they built an entirely new kind of database, a distributed key value store, in order to do that. And they didn't use Oracle. That's so wrong at this point in time, because they weren't getting any value from the model that Oracle gave them. They didn't need tables and relationships and all that kind of stuff. They just needed the ability for you to shop. Same for Google's Big Table and all of those early precursors. So now, as data set size is growing, we all know what happens in a relational store. As data set size grows, those joins become more expensive, less predictable, and we start to panic. We have that join bomb problem, which was demonstrated by the budgerigar. So now, in case of question or scale, we break glass, and the NoSQL guys come to the rescue. Now, funny thing about the NoSQL guys is, except for the graph databases, which are awesome and different, most of them are pretty similar. So there's a bloke called Martin Fowler, who used to be our boss back in the day, and he's a lovely guy, and he wrote a book with Pramod Sadlage called NoSQL Distilled. Really lovely book, quite thin. You can read it on the train over the bridge back to civilization. And and what? Oops, I'm off the camera now. This is off the record. Pardon me. What Sadlage and Fowler observe in that book is that a lot of these databases are very similar. So if you look at a key value store, or you look at a document store or a column store, they work really, really well where you have symmetric storage and retrieval patterns. So when you store a shopping basket, retrieve a shopping basket, brilliant. When you store a customer document, retrieve a customer document, brilliant. But when you want to know about what kind of customers in a certain age bracket in southern Sweden are buying on a cold, wet Wednesday night, those things can't answer that question. And that doesn't seem like a very difficult question to answer. It's the kind of question you might ask of a relational database and get an answer. But with most NoSQL stores, these so-called aggregate stores, the way that you would get an answer is you take a bunch of data out of the database, you process it, you compute across that data, and then maybe you get your insight, and if you're sensible, you put that insight back into the database. So these things don't work tremendously well, or at least you switch to a more compute-oriented mode when you're using these databases versus a query-oriented mode that we're used to. So let me exemplify that. Here's a very small database, and you guys, you humans, you can start to infer stuff about this database. So you can see that I've got some users and some unfeasibly young ages, and you can see that somehow there's an implication here that this guy is a friend with this person and a friend with this person. And you can see that this person is a friend of this person, and so on and so on. So you can look at that, and you can kind of reify out of this data some kind of network, right? Some kind of social network. Of course, if I delete this guy from the database, won't help me, and then go and remove, for example, this field here, Because the databases don't really know that kind of constraint. It's just dump aggregates in. Aggregates are independent. They're not linked. So it would be my job to go through the database and remove any reference to Jeff if I end up deleting that record. So you end up kind of reifying out a graph from some flat data. And this looks really simple, right? Because it's just, you just reify. Let me tell you, at Neo4j, that reify is what we call a graph database. And it takes 25 full-time engineers and 3 overhead in order to do reify. So it's a non-trivial task, right? In order to do that well and to do that fast. If you were going to store this stuff inside Neo4j, however, it just looks like this, where the relationships, the friend relationships in this case, are stored as first-class citizens in the database. And then in order to find who's friends with who, or indeed who is friend with who, on my laptop, which is a shiny, new, lovely laptop that I adore, traversing one of these relationships in a steady-state database costs me about 1/13 millionth of a second. So that's kind of cheap. So you can see that actually exploring deep paths or broad paths or whatever in a graph database is pretty cheap. If you want to find out what my friends of friends are buying, such that you can recommend those products to me, because that's actually quite a powerful recommendation. As soon as someone in your social network gets an iPhone 6, you're getting an iPhone 6. Even if you are some Linux weirdo, you're getting an iPhone 6. But, no, you're on Windows maybe now. Okay, still not on iPhone 6. Okay, apart from Johan, who we now have in the graph as weirdo, a weirdo from Linköping, which weirdly has a K in it, so where the sh comes from, who knows? But I got a bad feeling about this. You guys know that, right? I mean, for us, it's like Linköping. Anyway, K, no. So, got a bad feeling about this. What if we decided then to start selling things into our little social network? Well, actually, if you do that in a graph, it's really easy. You have some users and you have some products. In fact, in Neo4j, these would be nodes with label customer and nodes with label product. And you simply have things like this. Gaza purchased some headphones, and Sally purchased some decks and some headphones. And in order to find out what Sally purchased, that's going to cost you 2/13 millionths of a second in a steady-state database. In order to find out what Gaza purchased, 1/13 millionth of a second in this case. If you were representing the same data in this kind of flat aggregate structure, well, firstly, the modeling is non-trivial. I mean, do you have separate documents or aggregates for the products and the people, or you put lists of purchases within the people, or what do you do? And then what's your indexing strategy? What's your secondary indexing strategy? It's kind of difficult, right? So in this case, I've faked it up and said, like, these guys have links by convention out to these products. But again, if I remove a product from sale, or indeed I need to do a product recall, because it turns out these guys are like full of explosives, and we need to recall them for safety reasons. Figuring out who's bought these, it's remarkably difficult. In fact, it's going to be order n, because I have to traverse every customer in the database. No, no, yes, no, 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 yes, yes, no, and so on and so on and so on. And for thousands or millions of customers, that's a bunch of ball ache, to use the computer science term. In this case, if I want to find out who's bought these, I just look for the incoming purchase relationships, and a few 13 millionths of a second later, I know that stuff. So this is awesome. But it gets worse. The Star Wars theme continues here. It gets worse. What if I wanted to do not just things that I've bought, but things that my friends and friends of friends have bought? This is a join bomb nightmare for a relational database, and it's a computational irritant for aggregate databases. But in a graph database, to find out what my friends of friends have bought, 1, 2, 3, 4 13 millionths of a second in a steady-state database on my laptop, which is awesome. That's quite a hypnotic one. I've got a few more of those. Everyone likes the minions, actually, turns out. So we're at an interesting crossroads. So my colleague, Alistair Jones, drew this. It's a lovely kind of signpost of where we are. In the middle is the relational databases. We can carry on going down that dead end if we so choose. But actually, there's a bunch of other interesting choices. On the left, We have most of NoSQL. We have the aggregate data stores, the Cassandras and the MongoDBs and the Aerospikes and so on. And in that model, we're going to denormalize our domain into keys and values or into documents or columns or whatever it is. It's a simple data model. Some of those databases have great operational characteristics, but the queries that we can solve are literally store and retrieve symmetrically. If we want insight into that data, it's a compute job. So it all sounds really impressive when you hear people like the folks at Netflix say, yeah, we bring up 300 instances of Cassandra to recommend the right movie for you. And then I'm like, how many instances of Neo4j would that take? I'm like, a fraction of one? Like, I don't know, a 10,000th of an instance? Something like that? I don't know. It depends if you're running on a ZX Spectrum or something bigger. So, in this kind of model, in order to understand data richly, you have to do a bunch of processing on it. In the graph model, things are a bit different. In the graph model, we actually have a high-fidelity data model which we ask questions of. So it's a little bit similar to relational in a way, where we built a model and we ask questions. In the graph model, we also, in the graph world, we build a model, a connected data model, and we ask questions of it. And by traversing the data, the graph data, we find our information goals. So the model here is a richly connected data structure, and with inordinately more expressive power than any other kind of database. And instead of computing a solution, we query for a solution. So it's actually quite a low latency, no join bomb kind of query model. So people are doing this. There are a bunch of cases. And so firstly, we've got, I've got half a dozen or so people here that I'll clip through in a fairly short time. Telenor. This is a classic case of relational to graph minutes to milliseconds. So Telenor, you guys know. I mean, admittedly, you're a bit grumpy about this bit, but suck it up, princesses. They got the oil and they fled from you. You think you're hard done by? We had the oil. We gave it away to private interests. So, we're a little bit jealous too. The world's greatest telephone company, Telenor, and Neo4j users, have this interesting problem where they have users who belong to businesses, blah, 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 plans that have bundles and blah, 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 blah. A really kind of nastily intertwingled, that's a science word, kind of data structure, or at least naturally intertwingled kind of domain, where there's a bunch of rules about what services I can have based on the business I'm in, the business unit I'm in, the product I bought, the bundle that's within, the blah, 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 bunch of other rules. And in order to determine when I switch on my phone and want to access some of these services quickly or log in, it has to happen fast. I can't be delayed while some arbitrary query chunks away. And at Telenor, they used to have a relational database that did this, and it took ages. It just wasn't good enough. They switched to a graph, they switched to Neo4j, and now they can manage subscription plans and customers and users and accounts and all that kind of stuff just by doing graph queries. And that's a classic minutes to milliseconds kind of thing. So in this case, the graph is providing performance benefits as well as being a natural way to map the domain. Beamly. Second screen company, so founded by a bunch of the people who built BBC iPlayer. What they want to do is make TV social. I mean, actually, I think they make it antisocial because instead of sitting around the TV and watching together, we all now look at our iPads while we're watching TV. But they want to make sure that, for those of you people enlightened enough in Sweden to watch Doctor Who, that you can connect with me and Ian in the UK to watch Doctor Who live with us and enjoy that community. There are lots of harsh faces around now. Okay, for these two guys in Sweden who want to connect with me, and we'll talk later, who want to get with me and watch Doctor Who, none of these heathens are going to provide company for you. But through the magic of Beamly, you can connect to us because we have a shared interest in a particular TV show or brand, or if you like, through which we can now connect and interact. It turns out that Beamly had this problem where they were what they do is collect TV metadata. They collect metadata about TV shows, characters, actors, series. They also collect broadcast schedules across a number of channels and repeat channels across countries and blah, blah, blah. And they had a relational model that did this, and it sucked because it was slow. By the time you finally realized that we should all be talking about Doctor Who, the episode had finished kind of thing. It was also a pain in the arse to change. And their data model was changing relatively often, but it was logically a very interconnected data model that they'd have to do boring, old, difficult SQL schema migrations with. And that was causing chaos and downtime and all kinds of nastiness for them. These guys realized that what they actually had is a graph. They have a graph of TV episodes. They have a graph of linked list of schedules for channels which are interconnected because this episode of Doctor Who is actually a repeat of that episode of Doctor Who which was screened the day before, and so on. Then you have people that like various episodes or series or characters or actors. And you've got a graph problem on your hands. They switched to Neo4j, again, classic minutes to milliseconds, plus no more horrible schema migrations. And their stuff flies now. Again, it's like super, super quick. eBay, and particularly the service eBay Now, used to be a company called Shuttle. So it was a London-based startup who were acquired by eBay about a year ago. And they had this lovely, lovely quote that they told us that they ran their entire business, their core business, on 7 lines of cipher, and that's Neo4j's query language. They told us that down the pub, and they showed us the 7 lines of cipher. When we formatted it nicely, it was more like about 15 lines of cipher. Cowboys. But their core business actually is this. They aggregate the secondary market in couriers in a city so that when I buy that camera from Michael, I can choose when it gets picked up at Michael's house and, more importantly, delivered to my house. So before they were eBay, they were just doing arbitrary, point-to-point couriering. And, of course, that's a graph problem because graph theory is born out of a routing problem around the 7 bridges of Königsberg. So these guys took that, fast-forwarded it 275 years, and built this system whereby I can buy TAT from you on eBay, get it delivered to me at a time of my choosing by using the graph to do the routing. Now, in the old days, of course, they also had a SQL database. And they had this lovely story where the most perverse thing happened, that their shortest delivery was shorter than their longest query. Which is to say, the thing that happens in the real world took longer than the thing that happens on a computer. That shouldn't happen, right? Otherwise, computers are somewhat reduced in value to us as a species if they're slower than the real world. They flipped to Neo4j. And so typically what they used to do in the old days on the relational system is they'd get a delivery slot back from their system within 1 second. Apart from occasional pathologically bad ones that took about 17 minutes. In the new version, using the graph, they also get their answer back in 1 second. But instead of returning 1 delivery slot, they now return, the last time I checked, 74 delivery slots. So, I'll round up. The graph is 74 times better in this case. So they can give you delivery slots for several days because today's not convenient, I'm in Sweden. Tomorrow's not convenient, I'm still in Sweden. By the time Saturday rolls around, I'll be back in home. I nearly said London, and I'll be able to accept that at 11 a.m. on Saturday morning. These guys now, see this smile? This is the eBay bought us smile. One of their guys was complaining to me in the pub a few weeks ago that he didn't get enough time now to go to the holiday home he bought in New Zealand with his eBay money because he was too busy having eBay shuttling around the world in first class. I was just like, at that point, I was like, I should be a user of Neo4j rather than a producer, because I'm certainly not, I don't have a holiday home in New Zealand or first class tickets. Anyway, Accenture. Another logistics example. So Accenture built a logistics network for Europe's largest parcel network. And the problem that those guys had is that they were using a relational database and it wasn't going to deal with the volume of presents leading up to Christmas. So for one major Western European economy, Christmas was basically cancelled, which is the saddest thing. Oh. And so what they did, of course, they observed that routing is a graph problem. They're smart guys. So they moved their logistics thing. So logistics is awesome. I didn't realize this. I once worked in a parcel warehouse, like physically lumping parcels around, and it was shit. But I now learned the clever stuff that was happening on the conveyor belts up top was amazing. And so now you think, okay, you know, in the old days, you get a parcel home, you open it, I think, well, I don't really like this Scandinavian knitwear, I'm going to send it back. Now you can return your Scandinavian knitwear in the clickstream. So as this thing is rolling along the conveyor belt, you've clicked cancel, that event reaches the conveyor belt, and it gets routed differently on the fly. That's so cool. That's like Okay, admittedly, it's the very epitome of who needs this except for first world privileged people, but it's still quite cool. So these guys built this, kind of routing system, and one of the major couriers in Western Europe now uses it to transfer stuff around. Now, as I understand, I hear this secondhand, but the guy who architected this from Accenture was once at a conference talking about how they built it, right? Because it's quite an impressive thing that they've built and so on. And a guy from Oracle stood up and said, yes, but you can do blah, 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 blah in Oracle. And this guy had a lot of Oracle experience, the guy who built this system. He said, yeah, blah, 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 blah. Yes, you can. Yes, you can. You do this in Oracle. You do that in Oracle. You do everything in Oracle. Larry's awesome. Blah, 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 blah. Oracle, Oracle, Oracle. And I'm paraphrasing a little, but the guy who built this, architected this, kind of said, yep, while you've been arguing with me, my system has already routed 10,000 parcels. Sit down. Which I would have loved to have seen that. I would have given somebody else's right arm to have seen that. So, particularly the last bit, sit down. So then we've got Crunchbase. They've noticed, that entrepreneurs in Silicon Valley are all very incestuous and they capture all that kind of stuff. But perhaps most importantly, we have Mapillary, who are the creme de la creme of the Öresund startup, obviously. Again, so these guys are mapping the world through pictures. They know that the world is an interconnected place. They know that the images they're working with are interconnected. And, of course, they graph it. And how are people doing this? Well, they're building modestly sized clusters of Neo4j. These 3 machines, actually, because you don't need much for a graph. Graphs give you fantastic vertical headroom. And Neo4j clusters, and we've got all kinds of fun stuff going on in Neo4j, like, for example, Paxos. Yeah, that's how you feel when you build Paxos. That's actually Leslie Lamport right there in his youth. And so, people roll out stuff like this all the time, where they roll out clusters of Neo4j under a load balancer, and they solve single data center problems. And then they roll out multi-data center versions of Neo4j, and they run applications built on Neo4j that span continents. We didn't used to do this, but then Adobe said, well, we wouldn't put you in Creative Cloud. And then we were like, oh, shit, we'd better start working between multiple data centers. And so for the last couple of years, we've been able to do that. But Johan never quite recovered from that. That was bad times, right? Bad times. But yay, because Johan's damaged, and now we work around data centers. This is a good thing, right? This is like, where we are now. It's all happy. Graph databases are a thing. People are using them. It's fun and lovely. And minions. Look at the minions. Look at the minions. Smile. So now here's like the dark bit. So you can imagine now, like, you're now looking at, okay, graphs have done great, but now, the evil empire's after you. I imagine that Oracle has somehow woken up to the fact graphs are awesome, and they want to like kick us in the balls, metaphorically speaking. I'd love it if Larry could kick Emil in the balls. I would pay money for that. You would too, right? Yeah. So this is like the dark bit. So it's like, okay, look, we are not, the evil empire yet. We're kind of just like a bunch of scruffy people with minimal funding. And we're just trying to do good stuff. So what might we do? Because you guys are all building more and more ambitious stuff on graphs in the same way that you used to build more and more ambitious stuff on relational stores. So what are we going to do to make sure that your ambitions are met by our technology? So one of the things you might do is say, well, why don't you take like the nice bit of Neo4j, like the kind of cipher stuff. So this is Neo4j's query language. Three people in the room and myself understand this. The rest of you, even the people who build Cypher for a living, are like, I do not know what this query means. It's a Doctor Who query, so you have to be a bit of a domain expert. So what you might say, well, look, Neo4j, what you want to do is get that lovely Cypher language stuff, which is absolutely wonderful and kicks SQL squarely in the balls. So this is actually saying that, hey, database, find me a pattern where I have some character in a node, which has this name, that's the doctor, where I have that character has an outgoing appeared in relationship. Hey, Visio dude, this is like Visio, you get this. It's like a Visio arrow, outgoing appeared in relationship to something which is an episode, where I have a character, specifically called the Lady Cassandra O'Brien, who also appeared in that episode, and then find me, using that episode, merge in the fact that the Doctor prevailed in that episode and that Cassandra was defeated in that episode. So you're drawing pictures of your graph in ASCII art to express your intent. It's absolutely stunningly beautiful and lovely. Right? This is like Swedish design sensibilities all over, apart from the guy that built it was Argentinian. But you know what I mean. So obviously then what we want to do is take that like, green writing, which looks a bit like ASCII art for graphs, and chuck it on top of some major, put it on top of some like infinitely scalable, awesome store. So we definitely want eventual consistency, and we definitely want base, and we definitely want partitions and all that good shit, right? Obviously. You might have got from the Rafflecopter. Come on, do it. Ah, PowerPoint, weak. Damn it. Oh, there we go. But before you get too excited by that, there's a couple of guys I want you to meet. This is Professor Pete Lee, and this is Professor Tom Anderson. And they wrote the book, which is generally known as Lee and Anderson. And it's a really good book. It's about fault-tolerant computing. Yeah, there's a lot of blank looks here. Look, it's relatively entertaining as far as academic books go. Okay, but anyway, it's quite interesting. These guys are in a graph that I'm familiar with, actually. So it turns out that Tom was my undergraduate supervisor, and Pete was my PhD supervisor, which is nice. There's a bit more to this graph, it turns out. So it turns out that if you were to model this in Neo4j, for example, you would say that Tom created an undergraduate supervision arrangement to which I agreed. So there's modeling the entities, Tom, me, the supervision. And then at some point, we had the next event, linked lists, awesome. Total ordering of events, amazing. The next event was conducted by Tom, and I participated in it, and it was an end-of-semester review. Now, in that review, I told Tom that I wanted to do a PhD. So there was laughter, that was the next event, which Tom roared with, and it was targeted at me. Now, I have to say, I was a very diligent student. I was diligently in the pub 6 nights out of 7. But the final aspect there is that Tom negotiated a supervision arrangement with Pete Lee, and I agreed to it, and he accepted it. The final relationship in this graph I can only infer through an incredibly clever machine learning algorithm that Pete really must fucking hate Tom at this point. Anyway, sorry, I was meant to be talking about graph databases. So, this is really, leading on from the Lee and Anderson stuff, dependability is the quality of a computer service that allows you to depend on it. And it's built from these 5 kind of building blocks. Now, of these 3 building blocks, I have to say that I don't know a tremendous amount. That's not my thing. But I do know a little bit about these 2, availability and reliability. And it turns out that these are quite important to build a dependable system. In fact, so availability is that the system is available and ready to provide service, and reliability is the aspect of a system that means that you're going to get correct answers when you ask of it. In database terms, this is your database is there and working, and this in database terms means you're going to get the correct answers. The database doesn't corrupt your data. And in fact, there's some really, really brilliant, seriously, it's kind of disrupting my flow, this switch it on, switch it off again clicker. I really should get a new one. There's some really great work on this. So there's the FLP work on trying to figure out how to deal with distributed consensus with 140 process. There's a bunch of really awesome scientific work that's gone on about this. Effectively, in any distributed system, most distributed systems are, of course, asynchronous. You can only pick one of safety, termination, or fault tolerance. That's a really nasty trade-off because you want all of these. So it's the same deal as CAP theorem, right, where you can only pick 2 out of consistency, availability, and partition tolerance. You've got these kind of really interesting trade-offs to make, which really means this in graph terms. Somewhere between being available and being reliable, there's this scientific arrow called massive fucking trade-off. Now, I get paid to work on that, which is amazing. I shouldn't say that in front of you. Anyway, my job is very difficult. It's not exciting at all. So I do need to be paid more money just to get through Monday to Friday. Don't let that put you, give you any other. No, that's not me. That's some other guy. There we go. And so, should my system be reliable or available? And the answer is, it really depends. And if you think about the way an aggregate database would deal with this. So an aggregate database, if you've got, say, a database like, say, Mongo or Cassandra or something, which are good databases, right? There's also a good bunch of work going on there. What you have to agree on is eventually all of your replicas must agree on one value. So if I write into the record representing Johan, intelligence, poor. I need that to be replicated across all the replicas at some point so they all agree on one value. And that's a fair thing to do. In fact, I think MongoDB has that optimization already baked in. You put Yoan, it automatically gives you a free document saying intelligence poor. They're gunning for you, mate. There's some great stuff going on here. I think about, I look at things like React, and I think they're really clever about this. They care about causality. They care about ordering of events in a distributed system. I look at things like Cassandra. It doesn't care so much. Cassandra uses wall clock time to figure out which of the writes will win within a column. React has things like vector clocks and also has mergeable data types. So there's a lot of interesting work going on to reason about, in a distributed system, what thing happened first and therefore what the replicas will finally agree on. It's brilliant stuff. It's brilliant stuff. The problem is, in a graph, we go both ways. As you saw in my earlier example, I want to find out what Sally purchased, but I also want to find out who purchased the headphones. So I want to be able to traverse those relationships in both ways at constant cost, whichever direction, whether I go from head to tail or tail to head. So it turns out that that's not twice as difficult as getting consistency of 1. Consistency of 2 is very much more difficult, as I will satirize momentarily. I'm just going to use the space bar. It doesn't need a battery. So imagine this. This is, I think, captures a certain modern love story. So this is the United Kingdom, and we can see that we loves America. And in the database, if we had an aggregate database, we might model it this way. We might have a node. This is node ID 1. It's got some data, country UK. It's got some relationship data here. It says, like, there is a relationship called loves to the record with ID 0, and the direction is out. So it's So we're saying the UK loves the record with ID 0. You can see this is the record with ID 0. It's the USA. And we say, hey, that's nice. There's a relationship called loves from the record with ID 1. And it's inbound. This is nice. These two things are kind of consistent, right? They make sense. Both sides agree that Britain loves America. And that's a good thing if you don't want to find a fuckload of drones over your home. USA. See? We're so compatible. That's them. That's us, that's them, that's us. We are so good friends. Now what happens when these guys come along? So we have a long-standing friendship with those guys. But of course, they would love to meddle. So they send les hackers to hack into our system. And look what they've done here. Like, at the same time that we are amping up our relationship with the Americans, we're saying that we love you 100%. Brackets, please don't send the drones. These guys are over here saying, we've deleted your relationship with the Americans. They're going to send the drones. And so what does that mean for this guy? Because it's grayed here. Well, actually, I don't know what it means. Because I think, if you look from the Americans' point of view, we love you, don't bomb us. You look from the Brits' point of view, well, I don't love anybody. So it depends. If you traverse the graph one way, you find that we love the Americans and they won't bomb us. You traverse the graph the other way, and it's like, you don't love us. Here come the drones, boys. And so it's like, release the fucking bombs. This is a terrible thing, right? And all because of something, computer science, consistency protocol, oh shit. So what it means is actually we have to kind of revise some of our expectations about what it means to build a dependable distributed system when it comes to building graphs. And this is kind of a revelation to me. Because I just thought, Neo4j, graph database, whatever, stick some key value store underneath it and call it quits. No, because it turns out that you can't be eventually consistent because we've just seen eventual consistency equals corruption. And if someone acts on that corruption by sending the drones, you're really, really going to regret using that database. It can't be base over acid. It turns out that, again, if you want your data to be reliable, you want your data to be correct, you can't have soft state. You need to be right consistent. And indeed, it's not clear to me that I want to partition the data, because if I want performance, I need it to act as if all of the data is in a single memory space, because in Neo4j, all we do is pointer chasing, and that's what makes it super, super fast. And that is surprising. Not my kid, but it's... that's how I felt when this dawned on me, because it turns out that for graphs, reliability is far more important than availability, because the stresses that a graph places on a data store is far more demanding than we place on an aggregate store. Documents, keys, values, columns, easy. Graphs, difficult. But you know, you've heard of these scalable graph databases that use a key value store under the covers. They must work. No, they will corrupt data. So it turns out that this kind of thing, dropping Cypher on top of Cassandra, inevitably leads to corruption. So now we're in the final play. Well, obviously until J.J. Abrams comes along and replaces my CTO. Return of the Jedi. No, nothing. I've got nothing apart from I just fucking hate Ewoks. I mean, seriously? Why were they in this film? It doesn't make any sense. Stormtroopers, armor. Head to toe armor, sticks. Oh no, suddenly my armor is catastrophically failed everywhere and the sticks are really hurting me. This, I can graph this. This leads to Jar Jar Binks. And no one wants to go. This is the chink in the armor that leads to Jar Jar fucking Binks. This is not good. Anyway, so what do we need to do to kind of solve this? Well, we need to do some science, right? So we have to like figure out like some very, very difficult, challenging computer science stuff so that we can make graphs massively scalable and available and like support you guys when you are the next Facebook. We can't rest on our laurels and say, hey, actually Neo4j for today and the foreseeable future has more than got you covered because there are already people running on Neo4j with graphs larger than Facebook's social graph. So we have existential proof that actually between 0 and about 140% of Facebook, Neo4j works. But when you're 150% of Facebook, we still want to be there for you. So the stuff that we're doing. So we're changing the database, so at the moment it only stores many billions. We're going to up that to many trillions because you guys want to store every tweet, every character, every Internet of Things movement, everything. Our query language is changing. So our query language has some brilliant people working on it who are figuring out how to make a declarative query language faster than native Java. And we have better internals. So we've got a bunch of other clever engineering types working on this, working on things like lock managers and caching, and they're doing clever things about eking the most out of the I/O channel that we have. Neo4j as an ACID transactional database could be considered relatively slow for writes. Once these guys fixed up that stuff in 2.2, which is our current working release, actually we get on this laptop, which is lovely and beautiful, give or take 30,000 ACID transactions a second. That is kind of impressive, right? Even for big heavy metal processing systems. So you're going to get bigger data, queries that are just going to get faster, and more concurrency. How? Because Neo4j is graph native all the way down. There's no third-party data store under this, and I don't buy into the pluggable data store stuff because graphs are a particular model and it needs support from the query language at the top down to how we lay out those bytes on disk at the bottom, and all of that needs to be sympathetic for us to get those kind of impressive performance figures out, which we like. Thanks, Joey. And next, we're going to change things. We're going to do peer-to-peer clustering. We're going to have cross-machine, massively concurrent ACID transactions. We're going to do caching and graph consistency. We're going to do graph partitioning. We're going to do it all reliably. There's going to be like, there's a delectable menu of interesting, awesome, fun things that we're going to do in Neo4j, such that by the time you guys get to need it, it's going to be there waiting for you. We are not going to be the bottleneck in your ambition. We're going to be a step, or maybe half a step ahead of you as you guys grow and your ambition and your systems get better. We're going to get better with you. By the time you need petascale, we're going to have had petascale for at least a month. And we like that. For those of you that have a monarchy, I'd just like to have a small point of order. This is what's known as the Queen. If you're wondering about your own monarch, they are known as a Queen. Okay, just to get that straightened out. And so this stuff is not easy, right? This stuff actually is the hardest job I ever had. And despite the fact that most days I go to work and think it's the best job I ever had, it ain't trivial. In fact, many of the things that we're trying to do are statistically solve NP-hard problems well. And that is not at all easy. And we're not doing this stuff, though, because it's easy. We're doing this stuff because it's difficult and because your ambition won't be served unless we solve these problems. Because what we think is like, impossible is nothing. This is the tagline, right? This is not impossible is nothing with Jim Weber. This is impossible is nothing with graphs, actually. But, what the hell? So, impossible, Ali had this phrase, like, impossible is not a fact. It's an opinion. Impossible is not a declaration, it's a dare. Impossible is potential, impossible is temporary, impossible is nothing. So we're trying to solve these difficult, challenging computer science problems ahead of the curve, slightly ahead of the curve that you're driving us up, such that by the time you get there, it's going to be solved and your ambition can soar in the same way that our ambition currently soars. Now, if you're interested, we are actually hiring to work on some of these nearly impossible problems, and yeah, you could even get to meet this guy. That's my boss. He won't go. Oh, shit, he won't go. I'm on camera. Hi, Emil. So that's all I've got, ladies and gentlemen. Thank you very much for listening. There's a few of us from Neo4j kicking around. Come talk to us about graphs. Come talk to us about what you're graphing. We'd love to hear about it, and give us feedback. We'd also love to hear that. So thank you for your time this evening. I hope it will be beneficial.